So section 5.2 is linear combinations of normal random variables. Okay. Now I'm going to tell you in advance, when you look at the solutions manual, it makes these look incredibly complicated, and it's really not. Okay, so follow my method and not their method when you try and do it. So example 1, okay, is just let x be normally distributed with a mean of mu and a standard deviation of sigma squared. Okay. And a and b are just constants. Now, go back to what we learned in chapter 2 and tell me what will be the expected value and variance of the new random variable y, which equals ax plus b. Okay. So as you went back, remember, what were the formulas we used for this? So the expected value of y is really the expected value of ax plus b. Okay. What happened to that a? Using our rules for expected value. The a comes out, and what happens to the plus b? Okay, for the expected value, it actually just comes out as well. Okay, so it's just going to be a times the expected value of x plus b. Okay, look back up above at the problem statement. What did we use for the expected value of x? The expected value of x is our mean mu plus b. Okay, so that's just using our rules that we learned last week. And if I want to find the variance of my new random variable, okay, I say, okay, well, what happens to the a in the variance? It comes out, but it comes out as a squared. And what happens to the plus b? It goes away, because remember, if we just add something, we're just shifting our whole random variable up, and that doesn't change the standard deviation or variance. So it's going to be a squared times, and what was my variance of my existing random variable x? It was sigma squared. Again, just using our old formulas. So example 2 says if x1 is distributed normally with a mean of mu1 and a standard deviation, a variance of sigma 1 squared, and x2 is normally distributed with a mean of mu2 and a variance of sigma squared, with the 2 on it to tell us it's our second random variable. If they are independent random variables, then what are the expected value and variance of the new random variable y equals x1 plus x2? So the expected value of y is really the expected value of x1 plus x2. And what do we get to do with those expected values? Just add the individual expected values. That's so. Okay, the expected value for the first random variable is mu1. The expected value for the next one is mu2. For variance of y, that's again the variance of x1 plus x2. Okay, and what do I get to do with those variances? Or do with that? If we know that if they're independent, I can just add their individual variances. So it's the variance of x1 plus the variance of x2. That only works because they are independent. So that's sigma 1 squared plus sigma 2 squared. Now with that in mind, then we have rules for the linear combinations of normal random variables. Okay. So the first one is if, again, x is distributed normally, okay, then if y, which equals ax plus b, is going to be normally distributed with a mean of a times the mean mu plus b, and the variance is a squared sigma squared. Now notice, these are the numbers that we found in example 1. Okay. And we did that using our old rules. What's the only thing that is the only new thing that is introduced here? The fact that it is still normally distributed, which may not seem that exciting to you, but it's very exciting to mathematicians that I can do a linear combination of my normal random variable and it is still normally distributed. Okay. And same thing if I have x1 plus x2. It's still going to be normally distributed, but my mean is excuse me, mu1 plus mu2, and my variance is sigma 1 squared plus sigma 2 squared. Okay. And along with this, we've done this problem before where we said, okay, well now what if I have the mean? So x1 through xn are independent random variables, then my mean, x bar, is distributed still normally, and we figured out before that the mean would be mu, and the variance would have been the old variance divided by the size n. So again, we already knew these three formulas from our old rules. The only thing we introduced in this section is that these combinations are still normally distributed. And this fact is going to be very important to us for the rest of the semester. Anyone heard of the central limit theorem? Okay, so this is our central limit theorem. Okay, actually, look back up here. So this one said if x is normally distributed. This said if x1 is normally distributed. But on this one, notice, did it tell us anything about the distribution of x1 through xn? Okay, this is for any random variables. They didn't even have to start out normally distributed. Oh wait, no, it did say that there. We don't get to any random variables till the next section, sorry. Okay, it does say still normally distributed. Okay, so this now tells us the fact that when we take our average x bar, the variance goes from the original sigma squared to sigma squared over n. What that means is that your averages tend to be closer to your mean value, mu, than your individual random variables do. Okay, and we'll look at an example of that. Okay, so for this example, we have the weight of salt packets are normally distributed with a mean of 0.2 ounces and a standard deviation of 0.01 ounces. So we have that it's normal. We have mu equals 0.2 and sigma equals 0.01. Okay. So for the first example, find the probability that a randomly selected salt packet weighs between 0.19 and 0.21 ounces. So we're looking for the probability that x is between 0.19 and 0.21. Okay. We're not using anything new, just everything we've been doing in the last section. How would you find these probabilities? What do you need to do first? We need to standardize. So it's going to be 0.19 minus my mean of 0.2 divided by my standard deviation of 0.01. So less than or equal to x minus the mean over the standard deviation, and 0.21 minus 0.2 over 0.01. So this becomes the probability that z is between -1 and 1. Okay.
Just 68%? Or according to the first.
Okay. So according to the empirical rule, that should be close to 68%. Let's see, because it might not be exactly 68%, because the empirical rule isn't very precise always. Let's look it up really quick, because I don't remember how close it is. So it's going to be look up the 1, then look up the -1 and subtract them, right? Phi of 1 is 0.8413, and phi of -1 is 0.1587. Which equals 0.6826. So I could have used the empirical rule to say that I know that about 68% is between plus and minus 1 standard deviation. We can use the table to figure out that it's not just 68%, it is 68.26. So the empirical rule is very much about this much. So we have a 68% chance that our one packet is between 0.19 and 0.21. Okay. So the next one, find the probability that the mean weight of 10 packets is between 0.19 and 0.21 ounces. Not quite sure why it said 1.99. So find the probability that the mean weight of 10 packets is between 0.19 and 0.21 ounces. Okay, so to do this, what you need to do is you need to say, well, what is the distribution of x bar? Because x bar is no longer going to have the same mean and standard deviation. It's now going to be normally distributed. What is the mean going to be? Well, the mean stays the same, but the variance instead of sigma squared is sigma squared over n. Okay, so x bar has mean mu equals 0.2, and what is the standard deviation going to be? Because standard deviation is what I need to standardize. It's going to be the square root of the old variance. Now, they didn't tell me my old variance, but the old standard deviation was 0.01, so 0.01 squared divided by n. So how many packets did I look at? 10. You'll notice that I could have also written that. So sigma squared equals, for x bar, equals the old sigma squared over n. Then the variance for x bar, standard deviation for x bar is just sigma over the square root of n. Right? That holds mathematically. Okay. But if I put it in my calculator, I get that my new standard deviation is 0.00316. Okay. So I'm looking for the probability the x bar is less than or is between 0.19 and 0.21. Okay. So we do the same process, but now we have a new mean and a new standard deviation. So 0.19 minus 0.2 over 0.00316. So this is the probability that z is between negative 3.16. Oh, that's the z-value because I've already standardized, and 3.16. Right? And now we need to find both of those probabilities and subtract. So if I look at my 3.16, it's 0.9992, and if I look up negative 3.16, it's 0.0008. So the probability is 0.9984. So let's look again at what this means. So my original problem was if I pick just one packet, then the probability that I'm between 0.19 and 0.21 ounces, okay, is 68%. But now if I take the mean of 10 packets, the probability that I'm between 0.19 and 0.21 suddenly jumps to 99%. So your mean is always going to be that much closer, or your x bar is always going to be that much closer to your original mean. Okay, so there's not nearly as much variance once you start taking the averages. So let's try a few more examples of our linear combinations. So the mean pregnancy length, 266 days, is about 0.73 years. The variance is 256 days. What is the probability that a randomly selected woman who gives birth 4 times will spend more than 3 years of her life pregnant? Okay, and again, we forgot to say here that it was normally distributed. Okay. So what happens is a lot of other textbooks, when I copy these problems, they don't always say that it was normally distributed because it is in that section in their homework. Okay? But to me, it's a very big deal because if I didn't know that this was normally distributed, it could be exponentially distributed, it could be beta, it could be gamma, it could be something we've never heard of before. Okay? And so you wouldn't actually be able to do this problem. So on the tests and things, I try very hard to make sure I always say that it is normally distributed because otherwise you can't use the normal formulas.
So in real life, this would not be normally distributed?
If you didn't know, you couldn't just assume that.
I mean, but thinking about it, you don't know a lot of people that are like 150 days over 9 months. Right? So it would be like an exponential distribution more likely, right?
It wouldn't surprise me if this was normal, but the fact that's throwing you off is the fact that the variance is 256 days. And that seems really big.
Well, yeah, if you have an average of 9 months, then I wouldn't see a lot of people going 150 days past 9 months.
Okay, and so I actually looked at this problem. When I was writing it, I was like, the variance is 256 days. That just doesn't sound possible. But if the variance is 256, then what is the standard deviation?
16.
16. So really, people are only like 2 weeks above or below, which makes it now seem fairly believable. Okay? Because I thought that too. So our original mean is 266, and our original standard deviation is 16. Okay. But now if we're looking for the probability that the randomly selected woman who gives birth 4 times will spend more than 3 years of her life pregnant. Okay. So first of all, you have to look at this and you say, okay, well, what does giving birth 4 times mean? Okay. This means that really we have x1. So let's make a new random variable. Let's call it y, or any other letter you want to pick. But really it means you take the first pregnancy plus the second pregnancy plus the third pregnancy plus the fourth pregnancy, right? Why does it make sense to add the pregnancies and not just take the first one and times it by 4?
Because it could be different.
Because each pregnancy could be different. Okay. So if that's our y, then we can say, okay, well, what would be we know that it will still be normally distributed, what will be the mean of y? Okay, how could you find your mean of this new random variable? Well, we could take the first mean plus the second mean plus the third mean plus the fourth mean, right? So 266 plus 266 plus 266 plus 266 tells me that my new mean is 1,064. We also need to find our new standard deviation. And to find standard deviation, remember, we don't have formulas for standard deviation, but we do have formulas for variance. So I can use the formulas for variance and then just take the square root. So what would you do with the variances for each of those random variables? You would just add them together, right? And what is the variance for each one of the random variables? Let's see. The variance is 256. So 256 plus 256 plus 256 plus 256. And it happens to give me a nice number of 32. So we have a new mean, we have a new standard deviation, and our new random variable is still going to be normally distributed. Okay. At this point, once you have your new mean and your new standard deviation, it becomes no different than everything we did in section 5.1. Okay. So now I'm looking for the probability that y is more than 3 years or 1,000 at 95 days. So to do this, I need to standardize it, and I need to change it from a y to a z. So it's going to be y minus the mean of y over the standard deviation of y. Greater than, so 1095 minus the mean of y is 1064 over the standard deviation of y, which is 32. Let's see, it's a z value, so I'm going to round it to 0.97. Okay, and what do I need to do here? Okay, what happens if I look at my 0.97? That is a z value, so I'm looking for a z value of 0.97. That gives me a value of 0.8340. Is that correct?
Minus.
I need to do 1 minus that. So 0.166. Okay. So the probability that she spends more than 3 years of her life pregnant is about 16%. Okay. Questions on this problem? Okay. Again, the only new step is find your new mean, find your new standard deviation, and then do everything the same as we did in the previous section. So for example 5, like suppose that the soda pop in a 16-ounce bottle is normally distributed with a mean of 16 and a standard deviation of 0.25, and that the amounts in the bottles are independent. Okay, why would the independent matter?
So you can add up.
So you can add up your variances. Okay. Let's see, so what is the probability that there will be less than 95 ounces of soda in 6 bottles? Okay, so first of all, that sounds to me like I'm looking for the total weight in 6 bottles. Okay, so if I'm looking for the total weight in 6 bottles, then what is my new random variable? Let's just call it a W, just for fun. That's saying I take the first random variable plus the second random variable all the way up to the sixth random variable, right? And again, I want to add these bottles because it's not just the first bottle times 6, it is each bottle could be different, and that's why I need to make sure I am adding them. So my mean for W is I'm just going to add up each of those means. Now there are 6 of them, so it's going to be 6 times the old mean, which was 16, so it gives me 96. If I wanted to find the variance of W, okay, well, what do I get to do with each of the individual variances? Add them up. There's 6 of them. The variance before was what? Did it tell me the variance before? It told me the, sorry, I'm trying to find the variance here. It told me the standard deviation was 0.25, so the variance is squared. So 6 times 0.25 squared gives me 0.375. So if I want to find the standard deviation of W, I need to take the square root of that. Okay. And again, remember that we only have our rules for our variances, so you need to find the variance first and then find the standard deviation from that. So any questions on how we find our new variance and our new standard deviation? Sorry, our new mean and our new standard deviation. And we know that our combination will still be normally distributed. So now we're looking for the probability that W is what? Less than 95. So when I standardize it, now it will be W minus the mean of W over the standard deviation of W. Is less than, so 95 minus our new mean of 96 divided by our new standard deviation of 0.6123. So this becomes the probability that Z is less than 1.63. And if you look up 1.63 on your table, that is the Z value. And then I look for the probability in the middle. It gives me 0.9484. So about a 94% chance that there's less than 95 ounces. Wait. I just thought something was wrong. So less than negative 1.63. How about 0.0516? Okay. So I knew that 95 was less than my mean of 96, so I realized I should have had a negative Z value. So, questions on that problem once I get the right Z value? So for the next example, I asked, what are the mean and the standard deviation of the average amount of soda pop in 6 bottles? Okay, sounds like the last question, except that we are doing the average amount. Instead of the total amount, we're now looking for the average amount. And all I want you to find is the mean and standard deviation. So what would you do for this? Okay. We could memorize the fact that X bar is still distributed normally with the old mean and then the old variance divided by n. Okay. Or if you don't remember that, you could use your rules and figure it out. Okay. So X bar is really x1 plus x2 plus up to x6 over 6. Okay. So for example, when I find my mean, well, I add up each of the individual means. So it's my 16 plus 16 all the way up and divide by, so mean of X bar, and divide by 6. Okay, which is going to give me what? 16. Okay. And when I want to find my standard deviation of X bar, okay, let's see, so we said we just had to add up our 0.25 squared 6 times. But then when I divide by the 6, what happens when you try and bring a constant out? It comes out squared. So instead of dividing by 6, I now have to divide by 6 squared. But I added up my 0.25 squared 6 times, so it's really 0.25 squared divided by 6. Okay, so that's using the old rules that we know, or we can just memorize this formula by now, or memorize it eventually. So the mean for X bar is just going to be equal to the old mean, which is 16, and the standard deviation for X bar, well, that's the square root of the variance. So square root of 0.25 squared over n, which is 6. So 0.102. So for example 6, we have an animal shelter has a special facility for sick animals. Suppose there are 3 cats and 2 dogs in the shelter and have either cat flu or dog flu. Let X be the duration of cat flu in hours and Y is the duration of dog flu in hours. So X is distributed normally with a mean of 36 and a variance of 9. And Y is distributed normally with a mean of 41 and a variance of 6.25. So when we ask you, what is the distribution of W as the total number of pet days spent in the infirmary? Okay, so first thing you need to do is write your formula for what W is. Okay, so how could you write out W? What are we doing to my random variables X and Y? Adding them. Okay, and there are 3 cats and 2 dogs. Okay, so someone wants to do 3x plus 2y. Okay, but do you have any concerns with that?
Different cats and different dogs.
They are different cats and different dogs. So I can't just multiply 1 cat by 3 and 1 dog by 2. I need to do 1 cat plus the second cat plus the third cat plus the first dog plus the second dog, correct? And then if I'm looking for the new mean for W, what am I going to do? I'm going to just add up each of their individual means. So the mean for the first cat should be 36. The mean for the second cat should be 36. Third cat is 36. First dog, 41. Second dog, 41. Now let's find the variance for W. And what am I going to do for that? I just add up the individual variances because we said that they should be, well, I didn't say that. Let's assume independence. Okay, so we can add up the individual variances. So you say, well, what's the variance of the first cat? It is 9. Second cat is 9. Third cat is 9. Okay, and then the variance for the first dog is 6.25. Second dog is 6.25. So 39.5, which means that the standard deviation for W is the square root of that, or 6.28. And for part 2, what is the probability that the average time a cat spends in the infirmary is more than 40 hours? Okay. So I think it's the average of the 3 cats. Let's see. And then we forgot to say, number 1, when it said what is the distribution, we need to say that it is still a normal distribution. So for number 2, we're looking for the average of 3 cats. So we're looking for X bar. And it's still going to be normally distributed. The mean will be what? The mean is for X bar is the same as the old mean, which is, the mean for a cat is 36. And the standard deviation for X bar is the square root of the old variance over n. So the old variance for a cat is 9, and divided by n. How many cats are we looking at? 3 cats. So 1.732. So again, on all these probability statements, you just need to find your new mean and your new standard deviation. Because now I'm looking for the probability that the average is more than 40. So probability that X bar minus the mean of X bar over the standard deviation of X bar is greater than 40 minus 36 over 1.732. So probably that z is greater than 2.309. Now that's a greater than, so I am going to need to make sure I use the complement rule, so 1 minus, and I look up my z. Let me round that z to 2.31. .9896, I need to do 1 minus that. 0.0104. Okay, so we only have about a 1% chance that the average cat time is more than 40 hours. So, any questions here?